Welcome to today's discussion on the latest findings from NASA's Juno spacecraft, which has been orbiting and monitoring Jupiter since 2016. The Juno science team will give us a new glimpse into how Jupiter's atmosphere operates underneath the top layer of clouds and what this could tell us about other giant planets in the universe. I'm Raquel Villanueva of NASA's Jet Propulsion Laboratory in Southern California, and I'll be your moderator today. And our speakers are joining us from locations all around the world. To talk about the latest results are Lucas Paganini from NASA headquarters, Scott Bolton, Southwest Research Institute, Marzia Parisi, JPL, Karen Dewar, Weizmann Institute of Science, Lee Fletcher, University of Leicester, Alessandro Mora from the Institute of Space Astrophysics and Planetology. We'll be taking questions during the briefing, so if you're a member of the media on the phone lines, press *1 to be put in the queue. And if you're on social media, use the hashtag #JunoMission to ask questions. I'll now turn it over to Lucas.
Thanks, Raquel. These are really exciting times. Juno was the second mission selected in NASA's New Frontiers program. And since its arrival at Jupiter 5 years ago, the mission has made exciting discoveries that made us rethink what we knew about Jupiter, including better insights into the planet's composition, new images of massive cyclone sepulchres, and even lining in the atmosphere, not to mention the stunning new snapshots of Jupiter. One of the great things about this mission is the complete set of instruments that have allowed scientists to see through the top clouds all the way down to its core in ways not possible before. The good news is that a few months ago, because of this great progress and the fact that the spacecraft is in good health, NASA extended its operations for 4 more years. This is what we call the extended phase. So Juno will provide new observations that address new exciting questions raised during what we call the prime mission, and it will add a few flybys to 3 of the 4 Galilean moons, the volcanic world Io and the ocean worlds Europa and Ganymede. Jupiter and its moon are fascinating worlds, and they remain a top priority for NASA. But most importantly, Juno continues this journey of exploration as NASA and the European Space Agency get ready for the next generation of explorers, such as Clipper and the JUICE mission that will investigate these ocean worlds in more detail within the next decade. Juno is providing incredible scientific discoveries that inspire and innovate, and I'd like to highlight the great work of this team of scientists and engineers that make it possible. I'm really excited to learn more about the latest scientific results. So let's kick it over to our experts. Hi, Scott. Good to see you. What's new?
Hi, great to be here. Thanks, Lucas. Welcome, everyone. I'm really excited to share with you our new results and the excitement of exploration and discovery that is so common in all of NASA's missions, and Juno's no exception. Today's focus is actually going to be Jupiter's atmosphere in 3 dimensions, where we're going to look inside the planet and how that has led to a new understanding for us. Before I get started, let me just give a quick summary of how and why Jupiter is so important to us. So Jupiter is the largest and most massive of all the planets in our solar system. In fact, it's so large and massive, all the other planets could fit inside. And this size is one of the key reasons that it's really of high interest to us. Because it's so large and massive, it's thought to have formed first. So when we study Jupiter, we're taking a look at the very early part of the solar system. How did planets form? Where did we come from? How are solar systems made in general? This is really the first step. Jupiter forms first, and that kind of leads the way to the rest of our solar system. And the giant planets in general follow suit and probably form shortly after Jupiter. And so Juno is part of a long history that NASA's had to study the giant planets, partly for that reason, because it's telling us about our origins. And in many ways, we may actually have needed a Jupiter to exist in order for Earth to be created and for us to get life. And so over the years, starting with Pioneer, we flew by Jupiter and Saturn, and then followed by Voyager, and eventually Galileo orbited Jupiter. And then Cassini, which actually extended it, and we went to study Saturn in depth and went into an orbit there. And through those kind of history of missions, we are able to compare planets. And comparative study is really a workhorse tool of science. It's very important to understand the similarities and differences and be able to explain those with our physical laws or the laws of nature. And that's going to be a theme in what you're going to hear today, because we're going to compare how Jupiter's atmosphere works to the Earth, and in some sense, even when we look at Saturn. And the extension doesn't just stop in our solar system, because we're discovering giant planets elsewhere throughout the galaxy and other solar systems. And Jupiter is our example. And when we get up close, and this is the first planet we've actually been able to open up and look inside of, this is going to tell us a lot about how giant planets work throughout the galaxy. Now, Juno, the name itself, actually came from Greek or Roman mythology. That was the wife and sister of Jupiter. And mythological stories tell us how Jupiter was casting a veil of clouds around himself to hide his mischief, and Juno, his wife, was able to use her special powers to part those clouds, remove that veil of clouds, look down deep, and actually see his true nature. And in many ways, that's what our spacecraft does, and that's where the origin of the name comes from. And so what we're going to talk about today is a new understanding of Jupiter from the outside looking in. First slide, please. So here you see sort of a traditional view of Jupiter. It's got the great red spot, the common and distinctive zones and belts, those stripes, the brownish, orange, and white stripes that cross Jupiter's midsection. This was our view before Juno. This is what we kind of knew and grew and got used to. And this image was taken by Cassini, actually en route to Saturn. It was taken back in December of 2000. And you can see all these primary features that we kind of knew and associate with Jupiter. At the time of this picture, nobody knew how deep does that great red spot go. We knew it lasted a long time, but we didn't know how deep or how it really worked. The same thing for the zones and belts. And we had no idea what the poles looked like. Next image, please. And so Juno came along, arrived in 2016, and we got our first glimpse of the poles of Jupiter. And here you see an image, one of the early ones that we took. This is actually a composite of two images, because when you look at the pole, it's only half lit. So we cemented together two images so you could see the whole thing in full lit. And you see that it's the zones and belts are gone. It's covered with these giant polar cyclones. That was a big surprise to us. Later on in the mission, we used our gravity techniques to actually uncover that the zones and belt structure went all the way down and was detectable thousands of miles below the cloud tops. And so gravity represents one of the main techniques that we open up the planet and look inside. And we're really looking at the distribution of mass in Jupiter, and you can see it all the way down to the middle. Another technique is through our measurement of the magnetic field, because partway down into Jupiter, the hydrogen that's in Jupiter actually starts to behave like a fluid and metallic, and we can learn things about the magnetic field structure, about how Jupiter is structured underneath that surface layer or the top cloud layer. And then finally, the microwave instrument, which is really an instrument that's central to this discussion. We'll talk also about the gravity field, but the microwave instrument was invented literally for this mission. And what it does is it opens it up and shows Jupiter in 3D. It opens up and removes the veil of clouds and lets us peer into the secrets that Jupiter's holding underneath inside of its atmosphere. Next slide, please. And so today, what you're going to hear about is a number of topics. Marcia is going to talk about the great red spot, And I'll talk a little bit about how that's not the only vortex that has deep roots. I'll talk about the microwave results from this, from the Great Red Spot, and she'll talk about the gravity field measurements, and they complement each other in a very nice way. Karen will then talk about atmospheric circulation cells and how they're similar to Earth, but on a much larger scale, because Jupiter's a monster planet, 10 times the size of Earth. 1,000 Earths fit inside Jupiter. Lee will then talk about the zones and belts and how they evolve with depth. And Alessandro will talk about the polar cyclones, the stability, something that we've been monitoring since their discovery, and how they kind of evolve and some theories of how they get developed and form in the first place. And then we'll end the press conference with some of the latest images we've had. This one is an older image, but it gives you a very good example of the different perspective you get from a polar orbiting spacecraft, because the Great Red Spot is not where you usually see it in this image, and that's because we're up close and personal looking from a new view. Okay, so next slide, please. So let's start with the microwave instrument and what we're learning about Jupiter's great atmosphere and the vortices that exist inside of Jupiter. So you see on the left here a big image of Jupiter, and you see this big brown with the white arrows going around it. That is actually a barge-like vortex storm, even though it's not round like you normally think of. It's kind of stretched out, but it's the winds are circulating around in the counterclockwise direction. And on the right-hand side, you see how the microwave sees this. So we're almost using microwave vision that allows us to look down deep. And at the top layer of that, on the right-hand side, you see a visible light image, and you see a rough scale, 6,000 miles across. And the next layer goes down about 6 miles. It's actually 6 miles above the cloud tops. The next layer goes about 6 miles below the cloud tops. And then we just get progressively deeper and deeper. We're peeling the layers off like an onion, looking deep into Jupiter. What is interesting to us scientifically was that at the top we saw this, and it looks like a kind of a bright whitish hue, and then it's by the time it gets to the bottom, it's actually brownish, and this is compared to the background atmosphere. So this is showing you the different layers, but at the top, because it's whiter, it's actually warmer than its surroundings. At the bottom, when it's browner, it's colder. So there's an inversion. Something flips in the middle of this storm, and it flips somewhere near about 50 miles down. So this 50 miles down is about 10 or 15 miles maybe below where we think water clouds are forming. This is the water condensation level where water vapor turns into liquid and you form clouds. It's also about where the sunlight could reach to. It can't get much beyond that. And so what we're seeing is that this storm's roots go down past the water cloud, past where sunlight penetrates. That's very different than the way we think Earth's atmosphere works, which is largely driven by water clouds, condensation, and sunlight. It also is indication that the ammonia and water are being moved up and down. And so this cyclone was really one of our first views. We turned the spacecraft a certain way so we could get a map of this thing that you see on the right-hand side, and you can see that it goes really deep, about 100 miles, maybe 200 miles deep. And in fact, it's visible in our deepest channel, so it could even go deeper than that. The next slide shows another example of a cyclone. This one's a little bit more round, like you might expect when you compare them to, storms on the Earth. And here you see that the winds are moving around in a clockwise direction. So this is an anticyclone. It's kind of spinning around in the opposite direction that the previous one was. And again, if you look to the right, you can see how this evolves as we slice through the atmosphere with our microwave eyes. At the top, it's more brown than it is to the surroundings, so it's colder. And then partway down, it starts to disappear at about 50 miles, but there's a hint of it that might be a little bit brighter. And so we think that it goes down 50, 60 miles or so, and it's colder at the top and warmer at the bottom. So it's sort of the opposite of the previous one. One is a cyclone, one is an anticyclone. They're just different directions that they're spinning, and the inversion is opposite. The next image is actually the Great Red Spot. So this is, of course, Jupiter's most famous vortex. It's gigantic. This thing's the size of the Earth. It's been around for centuries. The early telescopes, images, and even hand drawings show that Jupiter had some giant storm in it. So we believe this thing is really old. How it lasts that long is a mystery. And in fact, some people thought, well, maybe it has deep roots. It's spinning around in the counterclockwise direction. But it is an anticyclone. This is in the southern hemisphere. If you go to the picture on the right-hand side, or the graphic part on the right-hand side, you see the top layer is, again, the visible light. Now this thing is about the size of the Earth. And as you punch down into the different layers, you see that it's colder, right? It's colder at the top and warmer at the bottom. So it's consistent with the anticyclone idea. And it's visible at the bottom channel, very warm, but almost the exact same dimensions as what it is at the very top. So somehow this route is going all the way down a couple of 100 miles. There's no doubt that the water, which plays a big role on the Earth, and the sunlight are important at Jupiter as well. But some of the other processes is linked to this and showing us that these routes go down deeper and pass right through the water cloud like it doesn't even matter. And so how that works is going to require new models and new ideas to explain. And so we couldn't see the very bottom of this. And one of the next speakers will be able to investigate that for us because she's using the gravity field to kind of put a complementary constraint on this great red spot. Even though it goes down a couple 100 miles or even a few 100 kilometers, it's still a really tall storm. It's a pancake because it's so wide at the top, but the depth of it is, that pancake is much thicker than what we would have anticipated. So Marcia, tell us about your stuff.
Thank you, Scott. Hello, everybody. Thank you so much for joining. I'm very excited to be here. So as promised, we now continue to talk about the Great Red Spot, as we have very exciting new results. Can I get my first slide, please? So as Scott said, the red spot is the largest storm in the solar system, and it has been continuously observed for at least 200 years, and perhaps even since the 17th century. Just a heads up here, I'm going to refer to the red spot as a vortex or cyclone or storm interchangeably, but they all mean the same thing. So the vortex is storming in the southern hemisphere of Jupiter, about 20 degrees below the equator, and it is wide enough to swallow the Earth. So this is a huge feature. Despite the wealth of information that we have about the winds that are surrounding the Great Red Spot and the dynamics surrounding the Great Red Spot, we know very little about its depth. So this issue has fascinated scientists for decades because some of them, they thought that the Great Red Spot must be skin deep, so very shallow features. Others thought that because of its longevity, then its roots must go much deeper than we see. And the Juno mission previously discovered that the jet streams in which the Great Red Spot is embedded, they are as deep as 3,000 kilometers or 2,000 miles. But how deep is the Great Red Spot itself? So if you can please go to the next slide. So Juno had the opportunity to answer this question when it flew twice over the vortex at very close range. And it did so flying very fast. Keep in mind that the speed of the spacecraft is tens of miles per second. Then ideally, if Jupiter was perfectly spherical, then the trajectory of the Juno spacecraft would be virtually unperturbed. And this unperturbed trajectory is here shown by the blue line. However, because of existing asymmetries and mass anomalies, such as the ones that the vortex is generating, then the local gravity tends to pull and push away the spacecraft as it flies over the vortex. And this creates sorts of like bumps in the road for Juno. And these perturbations generate a Doppler shift on the radio signals that we relay back to Earth. So in the next clip, we're going to listen to the Doppler shift on the radio signals after it's been converted to sound. So please. So you've heard the frequency going up and down, and keep in mind these fluctuations are very small. We're talking micrometers per second, or if you wish, these are 1,000 times smaller than the average pace of a snail. So these are very incredible, outstanding accuracies. And they are in part due to our instrumentation. In fact, Juno is the first interplanetary mission that is using X and Ka band radio signals two-way for planetary geodesy. And then the perturbations that you just listened to, we matched them to our model of the Great Red Spot, and we found that the best match was for a model where the Great Red Spot is a few hundred miles deep. Next slide, please. So our data indicate that the Great Red Spot is contained within the first 300 miles or 500 kilometers of Jupiter's atmosphere, and this is much deeper than the visible cloud level and also of the water condensation level. So in other words, the Great Red Spot is as deep within Jupiter as the International Space Station is high above our heads. So if we were standing in the eye of the cyclone, we would be immersed in it from the sea level to beyond the orbit of the ISS. So the Great Red Spot goes pretty deep, but it is still less deep than the jet streams that's around. So they go much deeper, down to 2,000 miles. And we're going to hear more about the jet streams from the next speaker, Karen. So Karen, please take it away.
Thank you, Marcia. It's very interesting stuff. So shalom, everyone, from Tel Aviv, Israel. And let's start. We can go to the next slide, please. So the beautiful banded structure of Jupiter's clouds are embedded in the east-west jet streams that are now going to be animated with the black arrows. And 3 years ago, using the Juno gravity measurements, it was discovered that the jet streams extend 3,000 kilometers deep, or 2,000 miles. However, these are just the winds in the east-west direction. And now, using the latest Juno microwave data, we were able to detect the three-dimensional circulation, meaning the up and down and north and south movement as well surrounding these jet streams. Now, to detect these movements, we used measurements of ammonia gas from the cloud level to about 200 miles, which revealed that ammonia is being carried up and down by vertical velocities, which are remarkably aligned with the jet streams at the cloud level. Now, the relation between the two is via atmospheric circulation cells, which are no strangers to us, as we have them here on Earth as well. Let's go to the next slide, please. Now, the atmosphere of Earth, illustrated here on the left, occupies 3 circulation cells in each hemisphere, which influence the cloud distribution and the climate system. On Earth, these cells extend from the surface to about 6 miles height. And with the new Juno data, we were able to identify similar cells on Jupiter, except that the Jovian cells begin at the cloud level and extend to at least 200 miles, and probably much deeper than that. This means that the cells on Jupiter are at least 30 times deeper than the equivalent cells on Earth. The Jovian cells resemble, in their governing physics, the middle cell on each hemisphere of Earth, called the Ferrel cell. The white arrows represent the jet stream in the middle of the cell. Now, different than Earth, which contain only one Ferrel cell in each hemisphere, Jupiter, being much larger, 11 times bigger than Earth, and rotates faster, its days is 10 hours compared to Earth, which is 24, contains 8 Ferrel cells in each hemisphere. The cells on Jupiter don't end at the surface, as Jupiter has no surface, it is a gaseous giant, and yet they are remarkably similar to the cells we have here on Earth. Let's go to the next animation. If we were to approach Jupiter and look below the clouds, we would see these circulation cells illustrated in blue, which stretch around the planet uniformly. Now we are zooming towards the alternating jet streams and the accompanied cells. Each one of the jet streams, which is visible at the cloud level, extends very deep and is surrounded by a circulation cell, which rotates according to the direction of the jet. In the orientation shown now, looking from east in the northern hemisphere, a jet blowing from west to east is accompanied by a cell that rotates anti-clockwise, and the jet blowing from east to west is accompanied by a cell that rotates in the clockwise direction. The discovery of these cells shed light on the unseen winds below the clouds of Jupiter. And speaking on clouds, the next speaker, Lee, will now discuss how the belts and zones visible at the cloud level change their character with depth.
Okay, thank you so much, Karen, and greetings from here in the UK. So decades of observations of Jupiter have been used to explore the famous belts and zones at the cloud tops, as we've just been hearing, and their organization by the powerful jet streams that Karen was just mentioning. So if we could go to the first slide, please. Now, a good example of this is the comparison between visible light and infrared light. So the visible image on the right-hand side here from the Hubble Space Telescope shows reflection from those colorful clouds, revealing what you might see if you could look at Jupiter with your own eyes. The image on the left is in the infrared, showing the clouds as dark silhouettes against the bright internal glow of Jupiter. And you can see that the cloudy white zones block infrared light, whereas the cloud-free reddish brownish belts, they let it pass straight through. So above the clouds, we knew that zones were cold, cloudy, and enriched in gases like ammonia, and that the neighboring belts were warm, cloud-free, and depleted in ammonia gas. But what was happening beneath these cloud-forming layers was still a mystery. Before Juno, we suspected that the bands and the winds that we see at the cloud tops were just the tip of the iceberg, with deeper and unseen phenomena at work down below these clouds. And part of Juno's mission was to determine what was happening deep within Jupiter's atmosphere. So if we can go to the next slide, please. So to understand how the belts and zones change with depth, we needed to exploit microwave light. These clouds are completely transparent in the microwave, and that allows us to peer deeper than ever before. And when we peered through this veil, we got a surprise. Now, ammonia depletion in the belts should make them shine brightly in microwave light, and that's certainly what they do in all the channels that sense shallow pressures. And those are the three slices that you see on the left of this animation. But the plot thickens as we start to move deeper below the expected cloud layers into the warmer, deeper atmosphere, as we do for the three microwave channels on the right. Now, sunlight doesn't get down this far, so we're truly probing new depths here. And we see that the belts that were shining brightly in the shallow atmosphere have become microwave dark, whereas the zones become microwave bright. And now all this is the complete opposite of what we saw at the cloud tops. And you can see this for yourself. If you follow one of those blue arrows from left to right across Jupiter, the bright bands become dark. The edges of the bands remain the same as those we see at the cloud tops, revealing that these belts and zones do go hundreds of miles deep, but that their character reverses as we go deeper. So let's go to the next slide, please. So we call this transition layer the Jovic line, and it appears to be located near the layer where the temperatures in the atmosphere are just right for water clouds to form, about 40 miles or 65 kilometers down below the visible clouds. Now, a cline is a layer within a fluid where properties change, and sometimes these serve to separate one domain from another. I'll give you an example. The Earth's oceans have a thermocline, which divides mixed surface waters from cold and deep waters below. Now, for Jupiter, this isn't a new idea. The legendary science fiction author Arthur C. Clarke envisaged the voyage of the Kon-Tiki balloon down into Jupiter's atmosphere in his 1971 short story, A Meeting with Medusa. He describes the balloon traveling down towards a Jovian thermocline and its associated bank of clouds. And we're playfully adopting that term here as well. In our case, the Jovic line appears to separate Jupiter's shallow weather layers with microwave bright, ammonia depleted belts from deeper layers of microwave dark, ammonia enriched belts that are down below the water cloud layer. More simply, the Jovic line may separate the cloud forming weather layer that we all know and love from the deeper abyss that lies below. Now, this unexpected result implies something is moving all of that ammonia around. Maybe it's the circulation cells that were just described by Karen, or possibly some other meteorological phenomenon at work within this deep atmosphere. What's clear is that the microwave light has really opened a new window onto Jupiter's dark, warm, and deep atmosphere, and that the results are really going to be challenging our understanding of this giant planet for years to come. Now, this is the story at the mid-latitudes on Jupiter. at least. And now I'm going to hand over to Alessandro, who's going to describe what's happening higher up in the polar domain.
Thank you, Lee, and greetings from Rome. So as you mentioned, we have an infrared camera on board Juno. And an infrared camera is a very powerful instrument because infrared is the light which is emitted from a body, while visible light is just reflected. So there is much more information in the infrared radiation. For example, they can tell the temperature of your body just by pointing an infrared thermometer to you. The other advantage is that in the infrared, just like in a spy movie, you can see your enemies in the dark if you wear some kind of infrared imager. And this is very useful on a planetary mission because in this way you can, for example, observe the dark side of a planet or regions where the illumination is very poor, such as the poles of Jupiter. Because in fact, thanks to this camera, which is called GIRAM, and thanks also to the other camera on board Juno, which is called JunoCam, Juno discovered a very peculiar, I would say unique structure on Jupiter, on the poles of Jupiter. Symmetric structures. Now, symmetry is really beautiful in science because every time you see something symmetric, you think that there should be something hidden below that is driving this symmetry, some kind of force, some kind of hidden mechanism or law, which you want to discover. And so I would like to get to the first slide. So right after its arrival 5 years ago, Juno discovered that there are regular polygons with cyclones at the corners, and those are at the poles of Jupiter. At the south, which is what you're seeing now, we have a pentagon with 5 cyclones at the corners and a 6th cyclone in the center. And in the north, which is not shown here, we have an octagon with a cyclone in the center. Each one, by the way, is larger than Texas, and the velocity are of the order of 200 miles per hour. And we were puzzled because, of course, we asked ourselves, how is it possible we will be able to observe them until the end of the Juno mission? And the result I'm presenting right now is that, yes, they are exceptionally stable, so we're still observing them. So after October 2021, the Pentagon, for example, is still there, almost unperturbed, is just rotated a little bit, 15 degrees. Now, at the Earth, we know that cyclones are very fast and they have a very short lifetime. How is it possible that at Jupiter they are so different? We think that it is because of the peculiarity of Jupiter. And I ask the next slide, thank you. So just like at the Earth, cyclones or hurricanes are pushed poleward, following a force that is called the beta drift. And this force is indicated by the blue arrow. This force is due to the rotation of the planet. So the first cyclone that gets to the pole, it occupies the pole, and the next ones are forced to stay at some equilibrium distance because the first cyclone has a rejection force, which is indicated by the green arrows. They keep them at a distance. Also, they interchange mutual forces, so they want to stay at equal distances, and those forces are indicated by the magenta arrow. So this way we explain the stability and the regularity, the symmetry of the cyclones. Next slide, please. So in fact, a study has been published recently to explain such stability and the number of cyclones. And the most important thing to me, this study is also able to explain the reason why we do have this kind of structures at Jupiter and we don't have them at Saturn. Because at Jupiter, we have just the right side of the planet, the right momentum, the right wind speed to achieve this kind of stability. And at Saturn, we don't have that. Final slide, please. There is a last consequence of this, as cyclones they talk each other. Because Juno observed that if one cyclone is perturbed from its action, then this perturbation is transmitted to the other cyclone because of this kind of elastic forces. You can think there are springs in between that helps cyclones to communicate each other. And after 1 year, this perturbation has gone from one side to the other. And this gets back to my initial question, and I'm done with this slide. So, will we be able to observe them until the end of Juno mission? How long will they stay this way? Of course, we don't know. Nobody knows. But chances are that not only Juno mission, but also the JUICE mission in the next decade will be able to observe such features, because maybe they are very stable. Their lifetime can last hundreds of years, just like the red spot. And because I mentioned the great red spot, it's time to get back to Scott.
Thank you, Alessandro. That was great. It's really exciting. The polar cyclones have been intriguing to me since we first discovered them. And of course, we can't see them from the Earth because we're looking, from the equatorial plane, and these things are only at the poles. And so it really took something high up in latitude to be able to see it, like Juno. And what we've seen here today is sort of a new understanding of Jupiter's atmosphere and how it works. And this all comes from Juno's technique of being able to see inside the polar orbit, and also our ability to look in light that really our eyes aren't capable of seeing, like infrared or the microwave vision that the microwave radiometers see, where we can see inside. So it's very important in science to be able to look at and extend the human eye into other wavelengths. And this new understanding applies equally to the individual vortices, like the Great Red Spot, as well as the zones and belts. Although there's really big differences, we see the vortices going down hundreds of miles, and we see the zones and belts maybe going down thousands. Maybe the brakes on those jet streams aren't really applied until they run into the magnetic field of Jupiter, which is deeper down. But it's just amazing to see how this evolution works, and the similarities a little bit between the zones and belts and these vortices is that the water clouds are playing a role. It's where these inversions start to happen. Something's special about water at Jupiter, just like sunlight, just like Earth, but these routes go right past it. And so somehow you have to be transporting ammonia and water and things deeper down after they're all gas, right? It's so warm in Jupiter down below there that stays vapor, yet they don't really mix up together. We've seen that the circulation cells exist. We've now got evidence of that. They're very similar to Earth, but of course there's many more of them because Jupiter's a monster planet. The Jovicline, which with Arthur C. Clarke almost envisioned in this idea, and we see this inversion in the zones and belts with this Jovicline, almost a little bit like Earth's oceans. And then finally, the polar cyclones that Alessandro just talked about. And we wondered, since we discovered these, how stable they are, what forms them, and we've finally got some progress and made some understanding of answers to some of those questions. Another big question is, how deep are the roots to these giant polar cyclones? And we hope to be able to actually determine that in the extended mission, because we'll be getting closer and closer to the North Pole in the extended mission, and eventually the microwave vision will tell us how deep the roots are to these. Now I'd like to just spend a little bit of time showing you some of the most fascinating new pictures that just came down in the last week from our last flyby of Jupiter. Next slide, please. So this image we call Bands of Color. It's made by citizen scientist Brian Swift. All of our data from JunoCam, this is a JunoCam image, is loaded onto a website, the Mission Juno website, and amateurs, citizen scientists, even professionals, and people from all walks of life, school children, go in and make these pictures and post them. And Brian Swift is particularly talented at it. You can see in this image, it's a very different perspective. The zones and belts that we've been talking about are just wisps on the horizon at the edge of this image, because you're looking at a very unique perspective. And then you see these two vortices, one in the forefront that's very large, and you can see these little pop-up clouds in there, and the grays and whites. And then in the distant, on the far left, you see a hint of another kind of cyclone that's reddish. And this is giving us this unique perspective. It's a very good example of how the storms are different on Jupiter. Next slide, please. Here's another one, also by Brian Swift, and these are called swirling storms. And so now you're seeing sort of a little bit of the smorgasbord that Jupiter throws at us. You have both the vortices vortex type storms that are a little bit roundish, and then you have these wispy swirling winds. This is in the north temperate belt, so it's in the northern latitudes, and you can see again these pop-up clouds, these little white clouds. There's almost shadows that are visible there, so you can see that those are resting above another cloud base. These things are where we think there's updrafts of ammonia, and it gets up such a high altitude that you eventually form ammonia ice clouds. And although they look tiny in this picture, Jupiter's immense. And so these little tiny clouds are still 25 to 50 kilometers across. So these are actually quite big by themselves, not nearly as big as, of course, the Great Red Spot. And then finally, another picture of Jupiter's storms is something that's just sort of clouds being stacked up on our north equatorial belt. Again, Brian Swift created a great image here, and it really shows a great example of how the images from Juno can look in and see different layers. So you can see the different cloud decks, even without the microwave vision. You can see that you're seeing a 3D effect here where the light tan and gray clouds are sitting above a pool of darker gray, and there's orange storms that are peeking out from underneath the dark. And so you can see shadows actually being layered on this, so you can tell the different altitudes. And again, at the very top are those pop-up clouds. And so these filamentary swirls are some of the most beautiful, almost Van Gogh-like artistry that Jupiter's exhibiting. Next slide is a sort of a teaser, and that is, this is Europa, actually. We just got this on the last orbit. It's taken at a distance of about 80,000 kilometers, so we're pretty far away. The resolution is still about 50 or 60 kilometers per pixel, so it's not the best resolution that NASA's ever obtained of Europa, but it was put together very craftily and very well by a citizen scientist named Andrea Luck. And this picture shows the albedo differences, the color differences that we see at Europa even close up. You can see the almost continent-like things. Of course, this is an ice shell. And what's also unique that we're really have an advantage of, that Juno has an advantage of, is that we're seeing a new region that we haven't seen before. The center of this image is really the North Polar region, and we haven't been able to see that. And so we look forward to next year about this time, we'll be flying by really close, just a few hundred kilometers above Europa's surface, and we'll get very high resolution images. But this one already is a tantalizing example and a taste of what's to come. And so with that, I thank you very much for allowing us to share our excitement and for your role in helping to share that excitement with the public. I turn it back to Raquel.
Great. Thank you, Scott. We'll now move into the Q&A portion. And remember, if you're a member of the media on the phone line, you can press *1 to get into the queue to ask your question. And if you're on social media, you can ask questions using the hashtag #JunoMission. Now, the first question comes from social media. We have Kevin on Facebook who asks, how fast is the atmosphere moving? Are they clouds or more like vapor?
So I'll just give you a very quick answer that what you're seeing are clouds when you look at the visible images, are mostly clouds, but you're seeing different layers. And so there is, but they're not all vapor. The clouds, of course, can be, have liquid because you've got condensation of water, you've got condensation of ammonia, you've got a couple different molecules in there that can create different layers of clouds, different colors. And they're swirling around. Now, when you say how fast are they moving, that's kind of a loaded question because the zones of belts are blowing in different directions. And at different speeds. And so it depends on where you look, how fast they're blowing. Jupiter itself spins around, even though it's enormous, spins around in 10 hours. So here it is 10 or 11 times bigger than Earth, and it's spinning around 2.5 times faster. For a little bit more specifics on exactly how fast the winds, I'd like to turn to Lee and let him talk about the zone and belt wind structure.
Sure, thanks, Scott. So it's kind of hard to get your head around some of the speeds that are involved in the motions of cloud features across Jupiter. But around the equator, we can actually look and observe with a telescope over just a few hours, and you can see those clouds zipping along from west to east or east to west at hundreds of miles per hour. Now, that's in the sort of horizontal plane. If you're talking about motions that might be going upwards or going downwards, they're much slower. You only have to have motions that are on the order of centimeters per hour in order to get these things moving up and down the ammonia cells as we're talking about.
Great, thanks for your answers. We have someone on the call line now. It's Elizabeth Howell from space.com.
Hi, thanks for taking my question. This one's probably for Alessandro. So I was reading your paper, and I understand from that, as well as your discussion, why the oscillations around the poles appear to be very stable in terms of those cyclones. But you know that you did see a new cyclone form temporarily in 2019. So can you explain how that happened within the context of all the stability?
Basically, the 5 cyclones are probably a configuration where they leave some kind of free space for an intruder to get in. But this intrusion may occur only sometimes because the configuration probably is stable at 5, maybe not so stable at 6, or maybe you need a very huge cyclones to get the 6th place. So either the 5 configuration is stable and 6 is not, so that if a 6 cyclones get in, it is rejected, or maybe you need a very big cyclones to get the 6th place and get a new stable configuration with 6 cyclones, like an hexagon. That we don't know still, because we need more observations and more events like this to develop a consistent theory for this.
Thank you. And up next, too, on our call line is Marcia Dunn from the AP.
Yes, hi. Question, I believe, for Dr. Bolton. I'm wondering, how many individual storms would you estimate that there are at Jupiter? And would you consider, from what you've been able to analyze so far, that the Great Red Spot is the deepest or one of the deepest is regarding its route? And you mentioned that you cannot see the bottom of the Great Red Spot, so I'm wondering how much deeper could it conceivably go? Thank you.
Okay, so I'll take the questions in reverse order because I'm not sure I'll be able to answer the very first one. How many storms are there? But the Great Red Spot, with the microwave eyes, right, the way we see through the clouds, we detected it in our deepest channel, which was a couple hundred miles down. Now, Marcia looked at the gravity field, and they're looking at, the concentration of mass that might be associated with that Great Red Spot, and looking at very sensitive measurements of the gravity field and the distortions of the spacecraft's path, as she explained. And that put a lower limit on it that said that at least the bulk of the mass that's associated with that storm is sitting in the first 500 kilometers below the cloud tops. And so we think we've bound the problem between the microwave. It's deeper than 200 miles, but probably not deeper than, say, 300. Now, that doesn't mean there's a hard route cutoff. I think it probably fades out gradually and keeps going down, but the bulk of the mass is sitting in above about 300 miles probably, maybe. And there's some error bar on that. Maybe it's 350 miles. We're not sure exactly, but it's still way below the water cloud. Now, whether that's the deepest storm, it's probably the deepest one that we've seen. I mean, there was another vortex, the one I showed first that I called the barge, that we see also in the deepest channel, but the signal's not as robust. And so we believe it was already starting to fade out. Whereas in the Great Red Spot, it was still really strong. And so we think of the three vortex storms that we looked at, that the Great Red Spot was the deepest. Now, whether that means it's the deepest in all over Jupiter, I'm not sure. And another candidate might be the polar cyclones. I mean, it'll be very interesting to see when we get to the top of the planet later in the extended mission, how deep those go. I wouldn't want to be too quick to guess that we've seen the deepest. But the Great Red Spot is the largest, and that makes it special by itself. And you might expect that it might be deeper just because of that. But I think it's a little bit too early to guess that. Now, the last question, and I'm going to open this up to Lee in a minute too, which is how many storms are on Jupiter at any given time? I have, I would say it's covered. I mean, if you look at the high resolution images from Juno Cam, the place is covered with just incredibly beautiful swirls, vortex storms that are around. Some of them are these filaments just blowing around. All those are stormy places. And when you look at all of them, you see pop-up clouds, you see up-down drafts. I mean, the zones and belts are driving things. The water clouds are driving things, the sunlight. I mean, I hate to put a number on it, but it wouldn't surprise me if Jupiter didn't have thousands across its body. And, if you were living on Jupiter, it would be a real difficult task trying to do a weather report. But Lee, maybe you can shed some light from your insights.
Yeah, I think you're on the right tracks there, Scott. I mean, when there are two pieces of information that might help think about how stormy Jupiter is. The first is that even from Earth, from a backyard telescope, you can see a whole smorgasbord of activity in the Jovian atmosphere. And talented amateur astronomers are able to track those individual features as they're moving around in order to reconstruct things like the wind field. And they're tracking hundreds of these tiny spots every single night. That's quite incredible. And the second piece of information actually comes back to the Juno mission itself. And that is the number of lightning strikes we're able to see covering the entire planet and actually getting more prevalent as we get up to high latitudes. And those lightning strikes are presumably associated with the separation of charge within thunder clouds, cumulonimbus clouds like we're familiar with on Earth. And they are happening all of the time. This world really is an enormous maelstrom of storm activity. And just like Scott, I'd hesitate to put a precise number of it on it for you, but thousands is in the right ballpark.
Thank you for your responses. Up next on our phone lines, we also have Bill Harwood from CBS News.
Hi. Thanks very much. I guess this is for Scott. Two questions. As someone who enjoys looking at the Great Red Spot with his telescope whenever he can, is there anything in the data so far that even hints at how it's managed to be stable for so long? Are there any guesses as to that and why it seems to be shrinking over the past few decades? And also, speaking of the polar vortexes, how does what's going on at Jupiter, how do we think that compares to what we see in the polar regions of Saturn, which is pretty bizarre too? Thanks.
Yeah, those are all really good questions, Bill. When we look at the Great Red Spot, of course, we've been observing it for decades with telescopes and NASA missions and Hubble, and then before that you had, even old telescopes that almost antique type things that were discovering it. And what Juno's able to do is we've sensed that it seems to be shrinking, and appears to be shrinking since, say, even the days of Voyager, right? And what we're doing is seeing up close what's happening while that shrinking is going on. And we see sometimes flecks of these red flecks of, I don't want to call them paint, but they're clouds or things that are getting caught up in that. And so the dynamics are sort of being studied, and we can see things are changing. I don't think the theory's very far advanced to the sense where we can connect all of that to the changes in the size, except that we're starting to see that there are elements of the dynamics that are telling us that. And the depth of the root may be a hint as to its longevity as well. You might think that something with a really deep root might be able to last longer. But keep in mind that, from the image that Marzia showed us, when I lift the Great Red Spot out, it still kind of looks like a pancake. The pancake's thicker than we might have expected, but this is not a storm that goes down into the middle of Jupiter. at least not that we've seen. And certainly the gravity field data doesn't suggest that. But it is have a deeper root maybe than the other vortices, and that may be part of its longevity. It's also trapped, sort of between these two conveyor belts. A lot of the vortices are sort of built that way. You've got the zones and belts moving back and forth in different directions. They're almost like conveyor belts of winds, and things can get sort of stabilized in between them, right? And like a ball bearing almost spinning around. And so I think all of those are kind of hints on the longevity. I'm trying to remember, did you have another follow-up question to one of those? Because you've stacked a few and I might have forgot one.
If Bill had a follow-up question, we can have him get back in the queue and he can ask it again, because we do have another caller on the line, and then we'll just get back to you, Bill, when you get on the line. Up next is Rick Lovett from Freelance.
Yes, thank you. My question is technical. I think I know the answer, but I want to be sure of it. How were the rotations, the circulations of the north-south belts determined? Is that Doppler on ammonia in microwave?
I'm not sure I'm following the question. It's how do we determine the motion of the zones and belts, the directions? So we're not really doing that on Juno, although we can get images that are spaced apart and measure some winds. But I'm going to let Lee take a crack at that. If I interpreted the question right, you probably will be able to best answer it.
Rick sounds like he has
actually, I think maybe I'm not the right person to. I don't think I'm the right person to answer that one. Maybe if you don't mind, Karen, I might come across to you. We were talking about how the motions of the zones and belts were measured from an ammonia perspective.
Yes, absolutely. So thank you, Rick, for asking that. Actually, what Lee showed is the microwave data, and we were able to interpolate these data as a movement of ammonia. So in fact, we find that in the poleward side of the eastward jets, we find peaks in ammonia. That means that ammonia is being carried from below towards the surface, the cloud deck, and on the equatorward side of the jets, of the eastward jets, ammonia is being carried down by these vertical velocities. And then we were able to model those vertical velocities with the measurements from Cassini of the turbulence in the atmosphere. And we were able to recreate the data using a model describing these circulation cells. So we aren't able to measure them using Doppler shift. I think that was your question, but we are able to model those velocities using the microwave data, which is quite an astonishing tool that we have here on Juno. I hope that answers your question.
Yeah, let me just add something, because now I understand the question. I did misinterpret it. And what you were talking about was the vertical motions, and I, for some reason, thought you were talking about the sideways motions. So it isn't done with Doppler at all. The microwave radiometer is a radiometer, which is broadband and doesn't have the spectral type information that tells us exactly the lines where you could measure a particular emission line and measure its Doppler. And so it's done the way Karen was discussing. There's the Doppler measurements are only in the gravity field.
Rick, I hope that answered your questions for you. Up next on our phone line is Marcia Smith from Space Policy Online.
Thanks so much for taking my question. And I apologize if I missed this earlier or in the press release, but Scott, could you talk about the health of the spacecraft? And I thought I heard you mention something about an extended mission. How much longer do you anticipate getting this kind of data? And could you also talk more about the citizen science component of this? It looks like you're getting an awful lot of good data out of that. And how do people learn about it and get to participate?
Sure. Those are great questions. So the extended mission just started this summer, technically August 1st. and we had completed the number of orbits that were in our primary mission. And the health of the spacecraft is excellent. Jupiter is a very dangerous place with a lot of radiation, and we were protected like a tank with a lot of armor. And at the moment, the shields are holding up. If I can borrow something from Star Trek, the shields are holding, and we're not seeing any real indication of degradation, which is great. And that really is a marvel and attributed to the great engineering that JPL and Lockheed Martin were able to put together and make sure that we could last. And so the extended mission is approved all the way through, I think, September of 2025. And that is about a bit more than 40 more orbits. And that's a lot. We will take a lot of radiation by the end of that. So I don't, we're going to keep our fingers crossed that we last throughout that. But it holds a lot of potential, not only the satellites and the rings, but we're going to get really far north because our orbit progresses in the extended mission. It gets twisted around by Jupiter to further and further north. The perijoves, or the close-up approaches, will be further and further north, and that's what's going to allow us to investigate all of these incredible atmospheric phenomena in the north. And the same twist of the orbit is what allows us to fly by the satellites. So it's just a great advantage to have something like that. And so the health and safety, or I should say the health of the spacecraft and all the instruments is still great. And so I'm really happy to report on that. Now, citizen science is really something close to my heart, so I really appreciate your question. We spent quite a bit of effort to try to make sure that we could connect to the public and allow them to share the excitement of exploration and discovery. And so there's a website, missionjuno.swri.com, and I think that you'll probably be able to get that out of the press release, or they'll post it here somewhere. But anybody can go to that website. It's the official Juno website that's at my home institution, Southwest Research Institute. The NASA website has links to it, I believe, as well. And inside that website is a place called JunoCam, or image processing, and the images are loaded up as raw data there. And then there's some tutorials that teach people how to take that image and turn it into an image of Jupiter or whatever it is that you want to do. A lot of the people are doing artistic things. Some are doing scientific things. Some of them are so scientifically important, they're making the discoveries for us. We've included them on our science papers. They've become science team members almost. But others are expressing themselves artistically, which is a joy to see. Or their imagination. I've seen pictures with astronauts sitting at Jupiter. I mean, it's something I want to do. So it's a great program. And what happens is they can process that data. And if they have questions, they can pose them and learn how to do it. We have experts that will help them. And then what product they make, the images they make, they can post also. Or they can take somebody else's image that has been made and modify it. So there's quite a bit of different levels of complexity that you can jump into depending on how much time you want to spend on it. And almost all the imagery that you see from coming out of Juno, these beautiful images, the animations and videos that we make, are all coming from these citizen scientists. So thanks for your question.
Thank you. And then up next on the call line, we have a follow-up from Elizabeth Howell from space.com.
Hi, this might be for Scott. Thanks again. Is Juno able to see any atmospheric changes from the recent asteroid strikes, the last couple of asteroid strikes?
So we looked at that, and it's still being worked. It was almost far enough along that I was going to include it in this. But I'm a little hesitant to say too much because the studies are not done yet, but we did take a close-up look, and we don't see a big mark from that. But I say it with hopefully you'll grant me the right to retract my words if somebody sees something and say we've got it. As soon as we have a definitive result, we'll certainly make that available to everybody and announce it. But at the moment, it doesn't look like there's a big signal that jumps out at us.
Great. And then up next on the lines is Hagen Warren from NASA Spaceflight.
Hi, everyone. Thank you for taking my question. My question is for Dr. Bolton. How specifically does the atmosphere underneath Jupiter's cloud layer power the cyclones we see on Jupiter, and how specifically do these intense cyclones form? Thank you.
I'm not sure I know all of the answer to that. This is something that we're just studying. How exactly does the cyclones and anticyclones get powered? And so, on Earth, the meteorology and the weather is very much connected to the water condensation, the water clouds, the sunlight coming down and warming the atmosphere. And it was expected that maybe Jupiter probably worked the same way, and no doubt those processes are important at Jupiter. But the fact that we see the roots going deeper than those, much deeper, not just a little bit deeper, but tens of miles, 100 miles beyond where the water is, tells us that there's another process going on. And we saw another hint of that early in the mission. We saw variability of ammonia and water probably going on much deeper than we expected. And the answer to that was part of what Lee discussed, where there's lightning going on all over the place. And there was a hypothesis that we put forth that there was something called mush balls that might be going up and down, transporting this ammonia and water. Now, that's like a mush ball is sort of like a Jupiter version of hail. We call it mush because it's a mixture of ammonia and water. It's kind of slushy, and then it has some sort of ice crust around it. And just like hail on the Earth, these things, can get down and still be intact, even though it's too warm for ice to exist. So on the Earth, you see hail land on your driveway. I live in Texas, so we see it pretty common. You got to hurry up and hide your car when the hail's coming. But it can come down and bounce onto your driveway or street or land on your lawn. And there's a chunk of ice, even though it's warmer than freezing out. And so the hail on Jupiter, which we might call mush balls, may transport things down and evaporate. Jupiter gets warmer as you go down. And so once you pass the layer where it's too warm for water to condense or ammonia ice to form, we expect that it should be all vapor. And the naive thought was, well, it'll all be mixed up, but it wasn't. So there could be energy things going in from underneath, but you probably also have something going on from the top that's maybe driving things down. I think that the data is so new that modelers and theoreticians now have to go work this out, and undoubtedly there may be more than one idea out there. I don't know, maybe Lee, you have another something you might want to add to that?
So yeah, you asked a really good question about the formation of these cyclones and how they last and how they're maintained over time. And I think the thing, we can bring that back again to our Earth-based experience. And you're familiar with the jet stream that whizzes around the northern hemisphere here on Earth and develops these extremely strong meanders that can pull regions of high and low pressure either side of the jet stream and form depressions that then shape the weather systems, certainly that we have here in the United Kingdom. So imagine that those jet streams on Jupiter only have to develop a very, very small wiggle or meander, and you can start to spin up a cyclonic depression on one side of those jet streams. Once they're started, it's actually quite hard to slow them down. It's quite hard to get rid of them because you don't have a surface on Jupiter that's dissipating that energy and getting rid of that energy. So they can just persist for a period of time until they interact with other storms and with the jet streams to potentially dissipate later on. So they start small, then they can spin up, and then they can last for a long period of time. But the crucial thing is that we then see them because of their effects on the environment. So they change the cloud conditions within them. They change the susceptibility of the atmosphere to these convective plumes, these thunderstorms that can erupt from the deeper layers. So cyclones, when they're there, start to create meteorology that we can then detect with something like Juno, or even with a ground-based telescope looking at the incredible dark colors within those cyclones. So really good questions, and I think you can see from my answer that we don't have a complete handle on it just yet.
Great, thank you for your responses. We also have a follow-up question from Bill Harwood with CBS News.
Yeah, thanks, guys. And Scott, the other question I was trying to ask was, for anybody on the panel, have you learned anything from studying the polar vortexes at Jupiter that shed any light at all into what might be going on at Saturn, or are these so dissimilar that there's just nothing much in common? Thanks.
Now I remember the question. Sorry. Yes, in fact, I'm going to turn to Alessandro in a moment, because he was reporting on another manuscript that actually looked at that and tried to say, how do I compare Jupiter and Saturn, and why does Jupiter have these polar cyclones and Saturn doesn't? And the answer had to do with the forces and just the way things were. But Alessandro, maybe you want to echo or expand on what you presented.
Yeah, thank you, Scott. So in fact, there is this new manuscript by colleagues of Karen that's been published recently, and it explains nicely the reason why we do have those kind of structures at Jupiter we don't at Saturn. So think, for example, at the Earth. Change the rotation speed of the Earth, you get a different meteorology. If you change the gravity of the Earth, you get a different meteorology. If you change the amount of energy the Earth gets from the sun, still you have a different meteorology. So every planet has its own key quantities, and these key quantities, of course, they impact on the meteorology. So the meteorology of Jupiter is so peculiar because Jupiter has the right size and the right wind speed and the right energy to get the size of the cyclones. They are big enough to maintain this kind of mutual rejection forces, but they're not so large to get just one cyclone. So actually, Jupiter is the perfect case to match the very simple theory that is at the base of the formation of theory of cyclones. And that's the reason why we do have at Jupiter. And so probably we will have this kind of structure even at every kind of exoplanet I'm dreaming of that are the same size of Jupiter and get the same energy. Exocyclones.
Great, thank you. And up next on the call line is Morgan McFall Johnson with Insider.
Hi, thank you. I think this question is for Scott or Marzia. I wanted to ask about the jet streams going so much deeper than the Great Red Spot. Was that surprising? Does it make sense for the jet streams to be so deep and the spot to be such a pancake in comparison? And do you have an understanding of why it's structured like that? Thank you.
Well, I can just tell you a little bit, but I think Marzia might be able to say a bit more because it is through the gravity analysis, and it was a colleague of hers and Karen's that published that paper, Yohai Kaspi. Now, when we look at the jet streams going down and we look at the gravity field, we see a signature. The jet streams and the zonal winds on Jupiter have an asymmetry north to south. In fact, the asymmetry on Jupiter is almost a theme of this planet, and some of it wasn't really expected. The magnetic field is asymmetric, the gravity field is asymmetric, and the atmosphere is asymmetric, and yet it's a giant ball of gas spinning around in 10 hours. And so a little bit of it is surprising that is able to be so asymmetric. But when you look at this and you see these jet streams going down and they're detected, this asymmetry was detected in the gravity field at a depth of about 2,000 miles. And then below that, we think maybe it was rotating around as a solid body, right? So above that, it's spinning around like on cylinders almost, where you're represented by the jet streams. Now, when you look at that a little bit and you say, okay, well, if there's a jet stream moving a lot of wind, a lot of the atmosphere down that deep, at some point when it gets deep enough, the magnetic field is going to be sensed. This magnetic field is starting to get stronger and stronger, and there'll be a layer down there where the atmosphere becomes more and more ionized and charged, so to speak. And when that happens, it's almost like putting the brakes on the wind streams or the jet streams, because now they don't just move around neutral atmosphere. If they're going to keep moving, they've got to fight with the magnetic field, which is a force to be reckoned with. And so that's part of why you might see those decay. Now, what stops the great red spot from going down that deep may also be, the layers get higher and higher pressure, higher and higher temperature, and eventually whatever's causing these may lose its ability to stay as an intact system. But it's not clear exactly how that works. And, somebody, an earlier question was talking about, how do you form these things? How do you form the vortex storms in the first place? And so there are people that are looking at whether, eddies coming up from beneath could actually play a role. And we don't necessarily have data that favors one idea versus the other, but that is a possibility. And so it could go, the great red spot, even though most of the mass maybe doesn't go much below 500 kilometers, there could still be things going on much deeper. Marcia, do you have any more on the depth of the zones and belts that you want to add?
Yes, Scott, just a brief comment. So she mentioned if this was surprising for us, and I would say in a way yes and in a way no, in the sense that I think most of the scientific community, they were thinking that the Great Red Spot was very shallow. There were two schools of thoughts, of course, between people that thought, it was going to stop in the first layers of the atmosphere, and others that thought that maybe it will even go all the way down to the center of the planet. So I don't think it was surprising actually to see it go so deep. And as Scott said, there are different things that contribute to the dampening of the flows. There are reasons that are related to the magnetic field and the uniform rotation at depth. And obviously there is something at 500 kilometers that is limiting the circulation of the Great Red Spot. So I would say, because we have these new measurements, then at this point, it's more kind of like reverse engineering. So we know how deep the jet streams are and how deep the Great Red Spot is. So can theoreticians explain why this is there is such a difference in the depth of the jet streams and the Great Red Spot, which of course are different. Also, the mechanism that govern them are similar but different.
Thank you. And we also have some questions coming in from social media with the Juno mission hashtag. Kate on YouTube asks, would the colors in Jupiter change with different temperatures?
I think I'm going to let Lee answer that because I know he's got a good answer.
That is an absolutely fabulous question. And, to this day, it's one of the embarrassments maybe of planetary science that we still don't know exactly what is causing the colors of Jupiter. Those beautiful reds and browns that we see in the cloud decks could be being created by compounds that contain things like sulfur, things like phosphorus in the cloud tops of Jupiter. But we don't know exactly what that signature fingerprint of that material might be like. So yes, if you start to change the temperature of the atmosphere, if you warmed it up a lot or if you cooled it down a lot, you would certainly be changing the composition, the blend of different species that are present within the cloud tops that are then absorbing and reflecting different amounts of light. I mean, I'll give you a good example. Say we started bringing Jupiter closer and closer in towards the sun. This would be bad news for us as human race, by the way. But if we did it, you would start to evaporate off those ammonia clouds. They would come back to become a vapor. And you'd start to excavate clouds from deeper and deeper down to the extent that those water clouds that we keep talking about would suddenly become visible. And a Jupiter that is covered in water clouds would appear maybe the same sort of whitish grey that you sometimes see when you look at the globe of the Earth when it's covered in clouds as well. So certainly the colors will change with temperature, and the reason is because the atmospheric composition will change as you turn that temperature dial up and down. So that's a fabulous question. I hope I've answered it for you.
Yeah, let me just add one thing to that, which is along this exact same line that you were saying, is that in fact, that's what we see, right? When we look at Jupiter and we see these beautiful swirls of different colors, we're seeing, in many ways, one of the things I described in one of the later images was you're seeing different cloud layers. And so those different cloud layers are different colors because of the composition changes, presumably. And that's changing because as I go down into Jupiter, the temperature and pressure are increasing. And so that changes what condenses where, what can exist, what the mixtures are, how it gets mixed up. So Lee's right. You know, if you moved it in, and I'm not a big fan of that because we'd have to leave. But you could, if you just turned up the heat. Now, also keep in mind that Jupiter receives energy and heat from the sun, but it's actually warmer in the middle because it's still cooling off from its formation. So it's radiating out heat more than it's bringing it in.
Fascinating to think of Jupiter as any other color than what we know it as today. We also have a caller on the line now, Leo Enright with Irish TV.
Thanks, Raquel. This is kind of a related question to Scott Bolton to do with the citizen science image, the swift picture of the northern hemisphere. Could you help us to interpret what we're seeing? I mean, if I saw this as a picture of the Earth or of Mars, I would say, okay, I know that's high, that's low, you know, that sort of thing. I mean, can you say what we're seeing here in terms of depth, or is that not possible?
Well, I can to some degree, not completely, but I mean, actually, if you look very close at that image and you blow it up on your screen, because it's pretty high resolution, you can actually see some of the shadows that we're analyzing. And when something casts a shadow, you'll be able to tell that what its height is relative to the cloud base that's below it. And I don't know exactly which image you were talking about, but one of them at the end that I showed multiple layers and sort of illustrated that example very well. And so part of our ability to look at that and determine the height of these things has to do with the shadows that we're analyzing. And we're just starting to actually, you know, develop models that can go in and really look closely at those shadows to try to put constraints on them. Because, you know, before Juno came along, we didn't see a lot of that. You didn't have these incredible close-ups that could tell you all of that. You had a little bit of it, but we're getting a lot of it. And so we're developing models now, and I'm sure, and there are probably scientists that are outside our team that are also playing that same game, because that's going to be very important to understanding the atmospheric dynamics. And sometimes, you know, the clouds part, and even with a visible image, you get to see down deep. And back in 1995, Galileo probe went in and measured Jupiter, trying to understand how its composition worked and what the structure was like and how temperature and pressure changed as you went in. And some of the results were very puzzling to us. And one of the results that came out was, well, it went into this place that we call the hotspot, warmer than everything else. Maybe there was a big downdraft, and some infrared images sort of supported that idea. I think today we look at it and we think, well, you know, those hotspots are in some sense a break in the clouds, and you get to see in to the lower layers, and the lower layers are warmer. But there may also be downdrafts. Why is there a break in the clouds? So I don't know if that's shedding the light that you were hoping for me to explain it. Jupiter's atmosphere is incredibly dynamic. It's not, I'm not describing a geologic landscape a little bit like Mars, where I can say, here's a crater, here's a dune. It's atmospheric dynamics of things blowing around, but there are different layers, and you can see those in the shadows.
Great, thank you for that answer, Scott. Now, that is all the time we have for questions today. Please contact the media line at 354-5011 for any additional or follow-up questions that you may have. And I'd like to thank the panel and all the people that called in to submit their questions. For more information on the mission, visit nasa.gov/Juno and missionjuno.sri.edu. You can also follow along on social media at NASA Solar System. Thanks again for joining us today.